Thanks all of you attended today's talk. Today, I would like to talk about how to use hybrid quantum classical computing for energy system management. So I'm Dr. Li Fan. I'm assistant professor at the technology division. And first, let me introduce our group research. So our group have two parts. First, we study the theory part. We study the optimization algorithms under uncertainty, and we also design quantum optimization algorithms. Then we also combine the classical and quantum computing techniques together, study these hybrid techniques. On the application side, our research mainly focuses on the power system operations and planning. Currently, we study how to coordinate the power and hydrogen systems, and we also study how to integrate the data centers into the power systems. And this is overview of my research. And so for today's talk, I will first introduce the motivation, the challenges of the large-scale optimization problems. Then I will give some short introduction of the quantum computing basics. And then I will introduce how we combine the quantum technique with the classical computing together. And then I will show a simulation result in the data center energy management system. And I will answer all the questions after I finish the talk. We have a Q&A session. So first, about the optimization. So in modern industry, we heavily rely on the mixed integer linear programming model to capture the physical operations of the physical system. For example, in power system, we use the mixed integer linear programming model to formulate the unit commitment problem. And we also can use this technique to capture the operations of the data center energy management system. And we can see in the next 10 years, we will have more and more data center in the power system, and the load will increase more than 10% from the data center. And for the mixed integer linear programming, and we can see here is the, let me open the pointer. So this side, on the right-hand side, we see we can mathematically describe the system as this x decision and y decision. X is the discrete decisions, and y is the continuous decisions. We use the linear constraints to approximate the physical constraints. So this is the mixed integer linear programming model, which is broadly used in the modern industry. And however, this problem is very challenging because generally speaking, MILP problem is NP-hard problem. It is very challenging to solve such problem. And here, there is a famous algorithm we developed called Banner's decomposition. So basically, the idea is that we divided the problem into two parts, the master problem and the sub-problem. If you look at the master problem, we see that we only have the x decisions, which is the integer variables, and this is a pure integer linear programming and with one single continuous variables. And on the sub-problem, we already got the x information, so we only solve the linear programming or convex programming for the y part. It's a continuous linear programming problem, which can be very well solved. The whole process is that we can solve the math problem by using the branch bound algorithm to get an integer solution, and we send this integer solution to the subproblem, and this subproblem can be solved by, for example, the interior point method or simplex method. And this, once we solve the subproblem, we can verify whether the integer solution is the optimal solution or not. If it is not, then we can generate the optimality cut or feasibility cut. We can put this cut back to the master problem, and this we can resolve this master problem. And when we resolve this master problem, we cut off the previous solution, we get a better solution. And by using this iterative process, we can cut off all the non-optimal solution and get the global optimal solution. So this is the Banner's decomposition. However, for this problem, we can see that the mask problem is still very challenging problem. The sub-problem relatively simple. We can, in the industry, we can very well solve it in very large scale. But for the mask problem, it's still a NP-hard problem, very challenging. So we still need to design computational efficient algorithm to solve this type of problem. So we are looking at whether we can utilize the quantum to help us solve this master problem. For sub-problem, it can be very well solved on current CPU, so we won't worry about that part. Like before we discuss how to utilize quantum to solve the master problem, let's look at the basics of the quantum computing. I will first introduce the superposition, the operators, and Hamiltonian simulation. Then I will introduce the quantum adiabatic algorithm. So what is quantum? Actually, we all are curious about the quantum qubit. A qubit can be represented in this way. It is a superposition of the state 0 and state 1. And for this state 0, we call it, here we use cat 0 and cat 1 to represent the state 0 and state 1. And for each state, we have a coefficient for it. We call it amplitude, alpha and beta. The alpha square represents the probability that the qubit will be in the state 0, and the beta square represents the probability the qubit will be in state 1. And we know that the total probability should be equal to 1, so we say alpha square plus beta square equal to 1. Mathematically, actually, we can represent this cat 0 and cat 1 in vectors. Here, cat 0 is 1, 0, and cat 1 is 0, 1. So we use linear vectors to represent the states. Then we have a single qubit representation. We are looking at how about two qubits? How about the two qubits interact with each other? So here we use tensor product to represent the two qubit system. Here we have psi and phi, two qubits. They tensor with each other, and then because we have two qubits, then that means we have four combinations. We have four states. They are 0, 0, 0, 1, 1, 0, and 1, 1. And for each state, it has its own coefficient, alpha 0, 0, alpha 0, 1, alpha 1, 0, and alpha 1, 1. Similar, we need to normalize it. So the square of this coefficient, the sum of this square coefficient should be equal to 1. That means the total probability should be equal to 1. So that's the requirement for the quantum system. So now we have a 2 qubit. How about n qubit? So let's look at the right-hand side of the slides. We have an n qubit system. It's a lowercase n. And for lowercase n, we have the total capital N states. Here, the capital N will equal to 2 power n. So for here, we represent the quantum system phi in terms of the sum of the n total n computational basis. Here, cat I represents the ith computational basis of the space, and alpha I is the amplitude of the ith computational basis. So in this way, we can represent the n-qubit system. So the n-qubit system can represent a very large space, right? We can see the space will be capital N, which is 2 power of n. And another visualization of the qubit is on this sphere. We have a single qubit can be represented on this sphere. Once we have a qubit and we use vector to represent the qubit, the next question is how we operate them, right? We want to operate this qubit and evolve the quantum system. So mathematically, there are some fundamental operators we need to use. We call it Pauli operators. Here, x, y, z, I are 4 Pauli operators, and these operators are matrix, actually. If we apply Pauli x on qubit on state 0, it flip 0 to 1. Mathematically, you can check this part. And if we apply x to 1, we flip it 1 to 0. And one more important operator is the operator. This operator is very important, especially if we want to discuss the optimization, then the operator will help us construct the Hamiltonian. Here, the z operator, if we apply the operator to state 0, then nothing will change, keep the status. If we apply z to 1, then we add a negative sign for the status, but we are still on the 1 status. So these are the Pauli operators for the quantum system. And another 2 important operator, one is the Hadamard operator. The Hadamard operator helps us create the superposition. So basically, if we are at state 0 and apply Hadamard operator, we will go to the superposition of cat 0 plus cat 1. So it helps us create the superposition. And similarly, if we apply Hadamard operator to cat 1, then we will go to the status cat 0 minus cat 1. So this one is very important because it helps us prepare the system on the initial status with the superposition. And one more important operator is the C0 operator. C0 operator actually work on 2 qubits. One qubit, we call it a control qubit. The other qubit, we call it a target qubit. So when we apply the C0 operator to these 2 qubits, the control qubit may flip the position of the target qubit. If the control qubit is 0, then the target qubit keep unchanged as the same. If we have the control qubit as 1, then we flip the position of the target qubit. For example, here in this example, the control qubit is 1 and the target qubit is 0. Once we apply this C0 qubit, then we get 1 tensor with 1. So we flip the 0 to 1. So this is the C0 operator. So the Pauli operator, Hadamard operator, and C0 operator are the fundamental operators we will use in quantum computing. Now, we have this basics, what is quantum qubit, what is quantum operator. Next important thing is what is quantum computer. So the fundamental part of quantum computer is that the scientists propose this idea, want to use quantum computer to simulate the quantum dynamics, because we believe it is very hard for us to use the classical computer to simulate the quantum dynamics. So we want to build or create the quantum computer to simulate the quantum dynamics. That's the main idea of the quantum computer. So for quantum dynamics, mathematically, if we look at here, the left-hand side of the slide, this is the quantum dynamics can be described by the Schrödinger equation. Here in this Schrödinger equation, we have the status of the system represented in psi t, and we have the psi t dynamically change respect to this Schrödinger equation is a differential equation. So based on the dynamic change of the ht is the time-dependent Hamiltonian, which represents how the system dynamic change. You can think about for given a quantum system, we have a kinetic energy plus the potential energy to represent as the Hamiltonian. And if we can solve this this Schrodinger equation in closed form, but generally it is very hard to get the closed form. We can see that at time t1 we have a status psi t1, and after we evolve the system will go to psi t2 at t2. And how do we get this status? Because we apply this U operator. This U operator actually is constructed by the Hamiltonian. Here, the function is an exponent function of the Hamiltonian of the system. So the U actually is the solution, closed form solution for the Schrodinger equation. However, in practice, it's so hard to get the closed form. So we want to build up a quantum system to simulate this, a quantum computer to simulate this quantum dynamics. One more thing is about the Hamiltonian. Hamiltonian operator is complex, but if you think the Hamiltonian operator, if we look back the Pauli operators, we see they are matrix, right? So in the financial dimension space, we can think the Hamiltonian as a matrix. For matrix, it has eigenvalue and eigenvector. So here on the right-hand side of this slide, I show you that H is the matrix, and this phi t is the eigenstate of the matrix, and this ET is the eigenvalue of the Hamiltonian. So this one is very helpful because if we measure the system, the ground state of the system, we can get the eigenvalue and the eigenvector of the system. So then we know this mathematics. So what's the intuition? How we use quantum computer to solve problems? So the idea is here on this figure is that, okay, give us a problem, which is problem fx, and then we can encoding our problem into a Hamiltonian. And once given us a Hamiltonian, we can encoding the problem Hamiltonian into the hardware, the quantum computer Hamiltonian. Then the quantum computer can evolve based on the given Hamiltonian. And after it evolves, we do measurement. We can get the ground state solutions, the eigenvalue and the eigenvector of the ground state of the Hamiltonian. So that's the key idea of the quantum computer. Let me repeat it again. The quantum computer do quantum stuff, quantum dynamic evolution. So we have a problem. We want to solve our problem. We need to embed our problem to this quantum dynamics. And after the quantum computer evolves the quantum dynamics, we can measure the system and get the eigenvalue, eigenvector of the ground state. This eigenvalue and eigenvector will be the solution of our problem. So that's the whole idea of how to utilize quantum computer to solve classical problems. So here, I'm talking about optimization. So let's look at how to use quantum system to solve optimization problem. Okay, so here is a very famous optimization problem. We call it a QUBO. The QUBO is quadratic unconstant binary optimization. Here is the mathematical formulation. The X is the binary decision variable, and Q matrix help us connect Xi and Xj becomes a quadratic formula. So this problem is a NP-hard problem. So the idea is that we encode this object function in the final Hamiltonian of the quantum system. So how do we do that? Mathematically, if we look at this blue part of the object function, we can map it to the here, the final Hamiltonian, the blue part at here. So this is the problem Hamiltonian. How do we mapping this formula to the problem Hamiltonian here, H final? So if we look at this H final, we will see, okay, we have Pauli Z operators. These poly operators actually represent the spin up or spin down, and it is a kind of binary decision. And this HI and GIG represent the coefficient of the system, and it essentially comes from the Q. If you can map it, the elements of Q will be used to construct this G coefficient and H coefficient. And in quantum system, the G coefficient represents the coupling strength between two qubits. And you might curiously, how do we get from F get such a formula? It's a very complex mathematical process. You can check the details on the book, but here I give a short introduction so that you have a better idea. So if we look at this poly Z operator, we apply poly Z on state 0, we get 0. If we apply poly Z to 1, we get -1. So we can mathematically write another formula to connect this function with operator. So poly Z is the operator, and here is a function. So this function actually represents those process. Let's check it. So if xg equal to 0, you will see the poly Z applied to 0 will get 1 minus 0. So it's 1, 0, right? If xg is 1, we will see poly Z work on cat 1 equal to 1 minus 2. So cat 1. So it is negative cat 1. So this is how we build up the relationship with the function and the operator. So if based on the similar idea, you can transform this function and encode it into this final Hamiltonian. So how we utilize this final Hamiltonian? Look at the formula here. So as I said, the Hamiltonian essentially is a infinite dimension space. You can imagine it is a matrix. So this matrix have eigenvalue and eigenvector. So here you can encode your optimal solution in the eigenvector and encode your object function in the eigenvalue. So if we can get the global optimal solution at the ground state, then we get the eigenvalue at the eigenstate, which is the optimal value of the object function. So this build up the connection from the optimization to the Hamiltonian simulation. So as I said, we encode our optimization problem into this final Hamiltonian, but the quantum dynamics start from the initial evolve to the final. So we need to further find the middle Hamiltonian. So we start from here, the right part, the initial Hamiltonian, which is a very easy Hamiltonian. We can prepare the quantum system at this position very easily, and mathematically we can construct based on the Hamiltonian on the initial Hamiltonian and the final Hamiltonian, use the convex combination to create this time-dependent Hamiltonian. By this convex combination, we have this time-dependent Hamiltonian. That means, okay, if we have a quantum system, we can prepare the quantum system at the initial Hamiltonian and evolve the quantum system based on the time-dependent Hamiltonian. And until long enough time, the quantum system will reach the point, the final Hamiltonian. Once we have the final Hamiltonian, we do the measurement and get the ground solution, ground state solution, the eigenvalue and eigenvector of the ground state. Then these are the solutions for our optimization problem. That's the idea how we utilize the quantum computer. So here we can see we call this algorithm called quantum adiabatic algorithm. There are 4 steps. We first encoding our solution. As I said, we encoding our target solution in the final state of the eigenstate of the Hamiltonian, and encode our target function in the eigenvalue of the final Hamiltonian. Once we encoding them based on some encoding rules, we can prepare our system at the initial Hamiltonian. But the initial Hamiltonian should be a very simple Hamiltonian, which can easily prepared by us. And once we have this initial Hamiltonian, we can create the time-dependent Hamiltonian, operate the system based on this time-dependent Hamiltonian. We can evolve the system from T0 to capital T, and when the system evolves to capital T, we get the final Hamiltonian. Then we observe the system, we measure the system, get the final ground state eigenvalue and eigenvector, which is the solution of the optimization problem. So this is the quantum adiabatic algorithm, which can help us to solve the QUBO problem. Of course, you can think, you might use your own idea to design other problems and apply your problem to this kind of algorithm. It's a very interesting topic, but today I will focus on this optimization topic. So once we know how to use quantum computer to solve the QUBO problem, let's see how we connect the quantum computer with the classical computer. So the idea, as I said, the idea is that we separate the problem, right? One part on the quantum computer, the other part on the CPU. So for CPU, we want to solve the polynomial solvable problem. Normally, it is convex optimization or linear programming. For the quantum computer, we want to use it to solve the hard problem. For example, the pure integer linear programming problems. So by using the iteration interacted by the quantum computer and classical computer, we can get the optimal solution for our original problem. So let's look at the idea again. So the idea is that we have a Bander's decomposition. For Bander's decomposition, we have a master problem, we have subproblem, and the subproblem gives us cut to help us cut off the integer solution, and for this master problem, we need to convert it to a QUBO problem. So master problem is the is a constraint problem. So we need to convert the constraint problem to the unconstrained problem by using the quadratic penalty, so that we have this QUBO problem. And once we have this QUBO problem, we can mapping or embedding this QUBO problem by using a Hamiltonian and get an Ising model. And for this Ising model, we can solve it on the quantum system by using the quantum adiabatic algorithm, give us an integer solution. And this integer solution will be provided to the subproblem. And the subproblems solved on CPU, we can get optimality cut or feasibility cut to help cut off the non-optimal integer solutions. So these slides give us the overview of how we embed the quantum computing inside of the Bander's decomposition framework. So let me quickly repeat it again. Give us an integer linear programming problem. We use quadratic penalty, get a QUBO problem. This QUBO problem can be embedded into a Hamiltonian. We call it a Ising model. And this Ising model can be solved by quantum computer by using the QAA algorithm. And this QAA algorithm gives us integer solution, and our CPU will solve the linear programming problem to verify this integer solution, whether it is a good solution or optimal solution. If it is not an optimal solution, the CPU will return us optimized card, and this card will add back to the master problem, and we resolve the master problem, cut off the solution, we refine the solution. By using this iteration process, we can get the global optimal solution. So another advantage of the quantum computer is that actually when we solve the master problem, we get thousands of samples, not one single solution. We get multiple solutions. Then we can pick up the top several solutions, like for example, top 3 or top 9 solutions. For each of these solutions, we can generate a subproblem, help us generate the feasibility card or optimality card. That means within one iteration, we generate multiple integer solutions, and multiple integer solutions generate multiple subproblem. We can then generate multiple cards. Then, because the number of total cards should be limited, right? If we at each iteration, we can generate multiple cards instead of one single card. That means we can reduce the total number of iterations. So that's the reason we designed this hybrid quantum multi-card Bender decomposition. At each iteration, we generate not a single card, but multiple cards. Okay, that's the idea how we use the quantum, how we combine the quantum computer and the classical computer together to solve the mixed integer linear programming problem. Now, let's see how we apply it to the data center energy management problem, whether we can see some advantage when we use the quantum computer. So for the data center energy management system, we know in the next 10 years, we will build more and more data centers. For data center, energy consumption is a big issue, and cooling also is a big issue. So for the data center, we have a CPU and GPU to consume electricity. And in order cooling down this system, we also need the chiller and the cooling tower and the ventilation to help us to cool down the system. All these equipment consume energy. So we want to minimize the total operation cost. When we build up the model, we find, okay, there are binary decision variables and continuous decision variables. For the binary decision variables, like we have battery, we want charge, discharge, and we have a chiller and cooling tower, we turn on, turn off them. These are the binary decisions. And for the continuous decisions, we need to decide how much power this chiller and tower will use. We need to control the HVAC system. We want to control the ventilation wind speed. So these are the continuous decisions. And for optimization, we also look at the constraints. For the constraints, we have the system level constraints like the energy balance. We want to balance the demand and the energy production. And we also need to control the room temperature, which is a dynamic process, but we use a linear algebra to approximate this dynamic process, build up the linear constraints to mimic this dynamic process. Besides the system level constraints, we also have the equipment level constraints. For each equipment, for the battery, HVAC, so we need different constraints to capture the operations of these equipments. So we also need to build up linear constraints to capture the operations of this equipment. In sum, this data center energy management system problem can be modeled by the mixed integer linear programming model. And for this problem, we can use the quantum computer to solve the problem. Then let's see the result. So here are two figures. The left-hand side, this left-hand side figure show at each iteration how much time the master to solve the master problem, it consume how much time. And we can see that here the black line represents the classical algorithm to solve the master problem, and the red line represents the quantum algorithm to solve the problem. And the red line and the black line, we can see we use more than 200 iterations. If we use multiple cuts, then we can solve the problem within 100 iterations. So that's the advantage of the multiple cuts effect. And in terms of solving time, we know that because we add more and more constraint to the more and more cuts to the master problem, as the iteration increase, the master problem becomes more and more challenge. So the branch bound algorithm will take more time to solve the problem. And for the quantum, it seems it's pretty stable, can solve it very fast at each iteration. And we also, on the right-hand side, we draw the figure to show the accumulate time. So we add the accumulate time to show the trend. We can see the classical algorithm show on this green line, it increased very fast. And the quantum algorithm, it seems it keeps linear increase to solve this type of problem. So from this part, we can see that quantum do show some advantage. And I have one more slide that, okay. We also can do some statistics to look at the performance of the solvers. So actually, branch-bound algorithm is very sensitive to the siting of the instance. We can see that on the right-hand side, when we look at the histogram of the solving time, we see it have a wide distribution for the classical algorithm, but for quantum, it's pretty concentrated. So we know that branch bound have this disadvantage. It's very sensitive to the parameters setting for the instance. Yeah, that's not a surprise for us to find such a distribution. And for the quantum computer is pretty fast, so it's pretty stable from our observation. And I almost finished my talk, and we published 3 papers regarding this topic, and 2 papers talk about the algorithm, and one paper talk about the application. So if you want to look at the details, you can check our publications.